Hello, ladies and gentlemen. Welcome to our surprise Sunday stream, which will cover for our Friday lecture, which I have to cancel on last minute because of personal issues that I will not be dwelling on too much. Either way, I wanted to cover some stuff that I wasn't able to do last time and continue, so you would have some more information that could be possibly beneficial for your projects that you're probably just starting doing now, because we know how life works. So, without further ado, today we will cover linear models. Last time we discussed general ideas covering the multi-parameter models and what's going on. Now we will focus on how these multi-parameter models are being constructed, usually by creating some kind of functional relationships for likelihood parameters, parameters of the likelihood function. For example, when we had mean in the normal distribution, we specified some kind of function of the mean that was more or less complicated. First, we will start with the most common idea, that is the linear model, and it's all generally comes to the idea that is being reproduced over the statistical literature, and generally is the idea of those called geocentric models, and it comes from this idea that there was a geocentric model of the universe, the Ptolemaic model of the solar system, that assumed that the Earth was a middle of the universe, the center of the universe, and the Sun was traveling around it. The main idea of the geocentric model, of course, was that it couldn't work as if the orbits were a circle. So people are complicating their models in order to fulfill the main assumption that the Earth is the center of the Earth by adding so-called epicycles, so that not only the objects were turning around the Earth, but also they were turning around additional. It was actually the middle of the circle that was moving around the orbit, and the planet was moving around that circle. This is called an epicycle, so that the middle of this circle is orbiting us around another circle. And in this idea, in order to correct for observation errors that were not consistent with the circular orbits, astronomers were adding more epicycles, and actually it became very accurate when predicting planetary movements. Why? Because adding epicycles is generally equivalent to extending a function into, in this case, periodic function, into a Fourier series by adding more and more of higher harmonics. And because those models were very accurate, and in many cases statistical models can give you very good predictions, but not necessarily mean that they are causal relationships. You just extended more information from the data that is consistent with the data, but does not really capture the actual behavior. And generally, in nomenclature, we have something called regression, and this is a bad term. This is a term that is very well entrenched in the literature of statistics, and also multiple other areas where they're using statistics, when it comes from the idea of certain things regressing to the mean, like for example when we are thinking about the height of children, comparing them to the height of the parents, then shorter parents have taller children, and the opposite, so that this height is regressing to the mean, and that was from the initial idea. And practically this name does not make any sense anymore, but it's so popular that it's completely irremovable from literature or practical use. Generally, Nowadays, by regression, we interpret the models that are used to explain relationships between independent and dependent variables in a statistical context, that we are having some kind of uncertainty and probabilistic representation. And we want to create models that are used to determine a numerical value that we can assign to our prediction in some kind of construction. And generally, the main idea behind this, what we call now linear regression, is the Gaussian distribution. And the main idea is that we want to model our relationship, our observed variable, as a normal distribution with certain standard deviation and certain mean, which we are uncertain about value of y, and we can express this uncertainty with a normal distribution. A normal distribution is generally very popular in the context of statistical analysis because of its simplicity and generally many observed situations that give the good justification of normal distribution. So, looking at this statistical model, we want to find a description of our uncertainty, of our relationship between information that we have and the outcomes that we want to observe or want to predict. So we want to describe this uncertainty. That's why model using normal distribution is so useful, because it gives us this uncertainty in a simple term of standard deviations. Generally, when we have a statistical model, this has it is the fact that we are using statistics is not necessarily the same as that we are doing something smart, because when we have a statistical model, even if we use complicated computational algorithms and we use complicated models assigned equal pairs, still if we gave them bad data, we will get bad results. And when we are using Bayesian models, our models give us probability distributions. So having data and our knowledge represented in the form of our model, we can capture our uncertainty, and using that probability distribution, we can simulate possible outcomes that will represent our uncertainty. So our normal model gives us tools, first of all, how to infer about parameters that relate our predictors with the outcomes, but also how to capture the uncertainty in the standard deviation. So we'll be able to sample from our normal distribution our predicted outcomes. So let's say, why Gaussians? Because generally Gaussian distributions are everywhere, because we have something called central limit theorem that says that if we have a sum of independently distributed random variables, the sum will be normally distributed. Sum is, among the others, the average of samples, because it's only it's a difference sum only by the scaling factor. And many phenomena that are happening in the world generally consist of sequence of growths or decreases that are happening over time. So let's start with a very simple, let's say, tough experiment, like Einstein was calling them. Let's imagine 1,000 of people, which we put in the middle of a football field. And then you have to make 16 steps along the white line in any direction do you want. You can change direction as you wish, and you can change the step length as you wish. So when we observe the behavior of these 1000 people, we have now question what is the distribution of their positions. And for convenience, we will assume that just this movement is distributed as a uniform distribution on the -1 +1 interval. So people are taking a no longer than a 1 meter step, and their movement is uniform. So it's completely equal probability of how long in which direction they move from the starting position. So when we start, we can observe we can observe those steps. So here everybody starts at 0. They take maximum of 16 steps, and as it would be expected, the more steps occur, the more broad their movements are. Each of these lines corresponds to one person that moves one or the other direction. And this is relatively simple behavior, but we can see, for example, at the 4 steps or 8 steps or 16 steps, how the histogram, so the cut at this point, behaves like. And as we can see, this behavior becomes more and more centered, that the sum of steps for each person, so their final position at the point of 4 steps, 8 steps, 16 steps, statistically behaves like a normal distribution. The more steps occur, the more normality we can observe here. Initially, it's less normal because it's very contained to the -4, 4 interval, so we have a lot of boundary values, we have no tails, but the more steps occur, the tails are more visible because it's less and less probable that everybody will move in maximum length to the one side or to another, and the concentration of the steps becomes here. So each person behaving individually, moving one direction, results as in the normal distribution of their movements. Hello to follow 0000. I'm very happy to have a big fan. That's a very nice words. But like I see, some activity in the chat is something new, so I'm very happy that something's going on. Either way, going to continue our train of thought. So that's why normal distributions are happening almost everywhere. And generally, normal distributions are very good for processes that come from the sequences of increments in growth. So for example, growing or economical behavior, or this is also true for small percentage changes, because it's that is multiplication by numbers close to 1. So like, let's say we move to 99% or we move to 101%. So like we are increasing by 1%, decreasing by 1%. Those behaviors are very close to normal because generally we are having effect that in case of multiplication, and these small percentage changes are a multiplication. In case of multiplications, we have normality but on a logarithmic scale. Why? Because if we take a logarithm of the we have a logarithm of this multiplication, we get of course sum of the value and this of the sum of all logarithms of all values. And in case of small percentage changes, we have the behavior that is traditionally, and I'll try doing something I haven't done before, but like hopefully it will work. So if we have small changes, small percentage changes, so we have multiplication by a 1 plus small number of percent, right? So we are multiplying our value. Then actually logarithm of this value is very well approximated by x. So this become the logarithms becomes this. So the sequence of multiplications by small numbers. So if we take logarithm by, so it will be one multiplication by another one, x2, and so on. Okay, that didn't work. And so on. So like we have a multiple like that. So logarithm of the product, of course, will become the sum of all those elements. Again, logarithm plus here. And this, of course, can be approximated by x1 plus x2. So, if we have this approximation, then of course for longer sums it will become. So then this becomes a sum of random variables and becomes normal distribution. But of course that is just a simple idea. So let's move to how to construct the model assuming this normality. So we start with the recognition of what is our set of measurements that determine the outcomes. So we have some outcomes and we have some predictors. So we have some values that we assume that will give us the outcome of our behavior, that influence the outcome of behavior. And determination of those predictors is a different case. We can work it in multiple aspects. One aspect which is popular in machine learning communities, just all the data that we have and see what happens. As potentially, if we have some issues, we can use some automated algorithms to drop something that's is less relevant by some kind of ranking algorithm for predictors, or we can use the expert knowledge. So we ask the specialist in the area, or we are the specialist in the area. So we select what are the measurements are in each of those. What predictors should influence our outcome, or we can try to experiment with some kind of hybrid approach that either we know something or we can estimate it. Or not estimate, but like we can guess, so give some educated guesses of what can influence. We can use some methods of, for example, causal analysis, which we won't be covering in this course, especially that the semester is ending. But the causal analysis is an idea that we compare multiple models of the same regarding the same idea with predictions, and we select by graph analysis what works the best. Then we define the likelihood for our model. So the plausibility of individual observations, or in, let's say, more technical approach for engineers, we define a function that evaluates how our model fits the data. In linear models, it is usually Gaussian, so it will be Gaussian distribution of measurements corresponding to our combination of predictors, which a logarithm of which will be a sum of squares of deviations between outcomes and linear combination of predictors. Using that, we can finally determine the predictors, define the model parameters, and choose the priors for model parameters. So creating such models requires us that we know what's the outcomes, we know how we want to compare outcomes to the models, how to which variables we want to use in the model, and assign them the appropriate parameters with the priors, because we are focusing on Bayesian analysis. And generally, construction of such models is very, very simple. We just assign that if outcome, so the outcome number I, has a normal distribution with some mean, also indexed by I, and typically standard sigma, some standard deviation common for all the measurements. If standard deviation would be differing for different measurements, then we have something called heteroscedasticity, which generally means that different measurements have different errors, and we have to correspondingly assign that. Usually this should be such our decision. It should not be a blind choice in a model creation, but it should be justified by observation or expert knowledge or something like that. And our mean, usually, if we have, for example, a single predictor, is a combination of an intercept, so a certain fixed baseline value for our phenomena corresponding to our outcome, plus the linear combination of parameter beta and certain and the value of the predictor. So we have this linear relationship between the outcome and the predictors with some base value, and we can assign some priors for that. Here we have a very, very broad prior assignment. We are assuming that we have some very wide priors both for alpha and beta. So and we assigned in this case an exponential prior for sigma. Exponential distribution is a positive distribution with positive values, with a bit heavier tail than the Gaussian, because the Gaussian has a square. Exponential doesn't have a square. Exponential distribution is the good distribution to model the it's a good distribution for modeling positive values, often used, for example, in the some kind of failure rates. But for standard deviation, it's actually very good because it allows you to, it assigns most of the mass in neighborhood of its mean, but it still allows you to get a larger standard deviation. You have no idea. Of course, there are different priors. You can use some half normal prior, or you can use some non-informative priors, or you can use some containment priors. It all depends on what you really want to do. Exponential is my preferred choice, but it doesn't matter that much if you have enough data. If you don't have data, then you have more uncertainty about sigma, which can be, of course, problem or might actually well correspond to your knowledge. Generally, what we have here are very weakly informative, a bit regularizing priors that says, okay, we don't know too much about the parameters, because as you can see, generally both of them can vary from -100 to 100 without it being surprising, and even one order of magnitude more. That's only who says that we won't have some absurd values of alpha and beta going into millions or something like that. And as we can see, mean is parametrically related to the predictors, and this is almost classical linear regression. In classical linear regression, that we are solving usually using the QR decomposition, so just an algebraic problem. Instead of all those prior distribution, we assumed it, and alpha and beta are the uniformly distributed, and we are not estimating sigma at all. We are not estimating sigma. We assume that sigma is known, and usually it's either assumed by some observation or so. This is almost classical linear regression corresponding to parameters alpha and beta. In Bayesian example, it is not that problematic. But why actually we want to use linear model? Because this is a bit arbitrary selection here. Of course, linear regression is everywhere, but we can accept that normal is a good idea. But why we really want this part to be a linear representation? Otherwise, other than that, this is a simple formula that is not problematic in its use. Well, this is the general issue in this context, that while linear models are simple, they are generally always, at least locally, decent approximation of any nonlinear relationships. In case of any nonlinear differentiable function, we can approximate it using this Taylor series expansion. So it always has these two linear terms that are corresponding to its representation, as long as it's at least once or twice differentiable. And in case of small variations in parameters, we have a very good justification that these models won't differ too much from the original function. In case of higher variety of parameters, then we have an issue, okay, how our model handles the variance from the linear model and the nonlinear behavior. But then we need to see if really is our model representation and model realization is actually is our data giving us enough information so that our modeling situation is, in other words, the issue is that if we do not have enough information to inform the linear model, it will be even harder with nonlinear model. So the problem is that if we have a lot of uncertainty in the linear model, then adding nonlinearity here won't remove uncertainty. It might be complicated situations. However, if our linear model is showing that it's really problematic, that it's not representing our data well, but still it's enough data that our estimates say that, okay, it's still very small deviation, then we can start to think about other nonlinearities. And let's do some linear modeling as an example. This is an example that was covered in our classes because you were given the idea of the model. This is the very well-known anthropological data set of Kang people. This is very is one of the nomadic tribes that live in the northern Namibia and southern Angola and Botswana, and this is one of the tribes that are really isolated from the mixing of population. So we have, like, say, some kind of the self-contained population that was being modeled. So this is, of course, this is just a popular data set. This data set is well published from the 60s. Is one of the examples in Richard McElrath's book. That was mine ideas to incorporate it here. But let's move to the model. We'll be doing as usually. We will be modeling using the command StanPy. We will be covering it using the Jupyter Notebook. Of course, we are using some standard inputs. There's my own utility functions. We are using, of course, command StanPy. We are using pandas for accessing data and stuff like that. In particular, I'm adding a ribbon plot from which I wrote myself. This is available in my in the repository in the old courses folder, and some visualization stuff. We are getting data from the Richard McElrath's repository, which is the Howell1 CSV, which we can, of course, get directly from online from the using pandas, using the read CSV function with the URL datasets. And we are focusing our dataset at the beginning only for the adults, because children will complicate our life even more. So we'll start with the adult modeling for adults. Using pandas, of course, we get this nice visualization here that we can see that our dataset includes height of people, their weight, their age, and their gender. And we will start with the simple case of linear model, a linear model without predictors. So it will only have a linear parameter called intercept. So mean will be intercept common for all the data, and we start with our model with some prior predictive checks. So we will see how our model parameters are assigned. So in this case, we are assigning the following. First of all, we assigned for the mean height, we have to assign some kind of distribution. And of course, height cannot be negative, so we have to assign some positive value. In this case, we took as an assignment an average height of 178 centimeters, and we've added a very big standard deviation for that. So we make that 67% of the sample should of our means from the parameters of the mean of the model should rely at 67% in the interval between 158 centimeters and 198 centimeters. So this is a very broad prior. If we add even more, if we look at the 97%, it's even more. And for the sigma, we are assigning the parameter of 0.067 for exponential model, and it corresponds to the mean of 1 over 0.67, which is 0.67, which is around 15 centimeters. So our standard deviation even gives us additional. So we expect that, and our expectation for the sigma is that 15 centimeters of standard deviation in the height measurements. So the measurements on average up to 15 centimeters, and general process incorporating on 67% of it, incorporating between 158 centimeters and 198 centimeters, and 97% twice as more. So that's right. So using our model for a predictive check, we compile it and we sample from it. To samples, we create 1000 samples, of course without any warm-up, because we have fixed parameters. Our model is not inferring parameters in Monte Carlo, it's just a standard. It's a collection of random number generators. So we sample normal for me from prior, sigma from prior, and then using those we sample predicted heights that we get with some assigned seed. So we have single chain, which just takes 1000 of samples, and we have our three variables here. A bit of matplotlib magic, and we can see that we have a very broad possible availability of the heights. Our error can be tremendous, so maybe sigma could be a bit smaller even, but at least it allows a very wide spread. And simulating our heights, we get the values that are, well, very well spread. We even get a single minus 50 centimeters, so maybe our prior is a bit too generous. And we got few samples going the world record of height of going 272 centimeters, which was the highest observed height of a person. And of course our mean is concentrated around the value that we expected, so around 180 centimeters, somewhere here. So okay, our model at least does not spew out total bullshit. Pardon my French. It gives some unreasonable values, but they are very separate. It can be assumed that when we add some data, this regularization will get us more into the actual mean of the population, and we can move to actual model for the inference, which is very, very simple. Again, we have to define we have to include information what data we are observed. So these are heights that are real numbers. We could specify that she shouldn't be negative, but that's less important at this moment. For our parameters, this is a depreciated notation. It would return warnings right now. This should be specified as an array. Either way, we have two parameters, me and sigma. That correspond to our distributions. We have the same priors as previously, but they are now parameters. So for parameters, we need to assign this lower equals 0. So this sigma is lower constraint. And of course, we are sampling from the model. Then we are using we are creating our model, and we are adding additionally generated quantities. So for each mi and sigma sampled for this conditional model, because this is now model conditioned on the data. So this generally will gives us a joint probability distribution for mi, sigma, and heights, all those three, the multiplication. But we are sampling for this joint distribution in order to get our conditional of mi and sigma on heights. And using each of the samples from the conditional distribution of mi and sigma, we can then sample height sample from our distribution. So again, compilation, and we are adding the data. We've implicitly put it here. So we are using function dict to create the two variables that will be needed, n and heights, in this form. So we have the default for chains, no issues are occurring, and we can use the Arvis summary function, which gives us that we got a mean of 155 centimeters, which fits our initial prior checks. It's just a bit somewhere here, so it's still well in the mass. Then we have the I have too generous mouse. We have sigma of 7, estimated sigma of 7.8 centimeters with some small standard deviations. As you can see, small standard deviations are very small here. Our standard, highest density interval of 94% density intervals are also very compact in this case, and we can observe here that samples for our joint posteriors of sigma and mi are a bit concentrated in this way, and we can observe that while our model is not terrible, we can see that our predicted height is not fully consistent with the observed height. As you can see, here we have these, on black we have the original histogram, and we can see that there are systematic differences that say that height in our population was not randomly distributed with a certain mean. There are also other factors that happen here because our model did not capture everything. So we can of course improve our model, and generally this flow of work is a good idea. Start with simple model and add predictors as long as it makes sense. So we see some certain problems, we want to add more. So the natural extension for our model is of course to add some predictors. In our case it will be weight. And for simplicity of our computation and prior assignment, we will be using something called centering of variables. So in case of our variables, we just want to specify that the weight will now not be represented in kilograms, but from the differences from the mean of the entire sample. And why is this beneficial for our case? It is beneficial because this gives our intercept in our model some interpretability. Because now our model has two parameters, or three, but sigma is like has a different meaning. The alpha will be mean. The alpha will be the intercept, so it will correspond to a situation. What weight is average for our people as long as beta time height is equal to 0. In case of uncentered variable, then it doesn't make sense because weight will never be 0. If we use centered weight, then interpretation of alpha, what is the average height of people when they are of average weight? So this now makes a bit of sense, gives us some interpretability for the coefficient. And instead of weight, we just think about the deviation from the mean of weight of the population. So we still leave for our alpha with our very wide prior here, because it being wide did not introduce any problems for us. Then for beta, we are adding the rather wide normal prior of having 10%, and our model gives us that for each height will be a normally distributed with sigma combination of weight times beta plus alpha, when weight of course will be our centered weight, which we'll provide here. So we are adding in our model, we have 50 samples, we have centered weight, which we will just sample from. We were not using real data, we're just using some artificial data. Will be linear values from minimum weight and maximum weight that was observed. So we just take all the possible values of weight between minimal and maximal centered weight. So something negative, something positive. Okay, and for our model, again, we are sampling with the same data. We still, because it's a prior model, we do not use the our model is of course fixed parameter models, so we sample it and we can plot something, and we'll plot how the relationship between alpha and beta will look like according to our model. So we are checking what are the possible relationships between weight. Now it returned to its normal values, so we've added the mean so it will look more interpretable. So using our model, we have now the relationships between weight and height that are possible for our model. And we can already see that this model does not make sense. That's why prior predictive checks are very important, because we can add the we can verify how our predictor works, and we can then we can see that aren't we too generous with our model. And certainly we have a problem that for smaller weights it proposes negative heights. So this is absurd. This is also absurd. We get too large heights that to make it any kind of sense. We are extending well above the possible values, even for below zero of heights and above world records very easily. So we need to change our prior in order to, for example, avoid a situation that we can see very prevalent here, that higher weight would correspond to increasing weight would correspond to reduction in height. So for that, we need to add a prior that will keep us from, would allow us to get the values of that will give us only the positive relationships, that increasing weights increases the height, because that's kind of makes sense. So the proposition is to use a log normal distribution, which is as a prior for beta, which gives us the standard which is a normal distribution on a logarithmic scale, but it always results in positive variables. So using this model, we see again prior predictive checks with the log normal distribution, and as we can see, we are sampling it again. We are getting samples, and now our model makes much more sense. There are still very rapid growths, but they are very scarce, and most of our results fit well into the reasonable interval. So we don't have a lot of absurd values. We have some of them, but again, we can assume that having positive slopes and reducing a bit standard deviation, it still gives us the more sensible priors to be more sensible priors looking at the predictions of height. We still have a lot of a lot of very tall people here, but possible, but we still, most of them are here, focused here. If we verify how our predicted heights look, so including our uncertainty modeling, we can see that our prior certainly assumes a bit too high mean height corresponding to our data, because this is here, now we are looking at the actual data, we are corresponding them to the prediction of data. We are using, again, a ribbon plot, so a plot of quantiles. The darkest here is median, there is, then it's a 40-60%, 30-70, and so on and so on. So we can see that our data is, let's say, according to slopes, it's reasonable, but mean is a bit too high, so perhaps we could reduce it a bit, but then again, we don't have much justification because of lack of expert knowledge about the, except of those data. We don't have an anthropological knowledge about Kang people that we could give some better predictions other than that, than our preconception about human height. So again, we move to our model. Our model now adds parameters alpha and beta. In order to the model look efficient and similar to what I showed previously on presentation, we are using the transformed parameter block, which will now add the mean as a multiplier of weight times beta plus alpha. So for each set of original parameters, we'll create these auxiliary parameters that we can then use in our model. This just makes everything more simple because we couldn't define it here in the model. So that's why we need to use it in the transformed parameters block, because otherwise different types of mathematical operations will be assigned during the compilation of it. So that's why it has to be constructed like this. Again, log normal distribution here. We are sampling the the heights using the code here. I think that's okay. We've got over the size limit. So okay, we've opened the editor. We just see that it's a for loop. So that's why it was the start of the for loop wasn't visible. So we start with the star model here. We compile it, it works. We've compiled it again, so just actually I'm not sure what's going on here. Maybe some artifacts from some testing. We are checking for 150 initial samples from the data set. So we create our model and we do some sampling. We see that the relationship between the beta is now very constrained to the interval between 0.78 and 1. Sigma is smaller, so we have the uncertainty of average 5 centimeters in the measurement, and our mean is still relatively similar to what we had before, but with even less uncertainty. The standard deviation is 4 millimeters about the average. So as you can see, in case of we can get samples of our mean. So we can get, this is the samples of parameters alpha and beta in order to get the mean, and we can see how this mean relationship gives us the what our model thinks that this is the underlying phenomena. Remember, here we assume that mi is an underlying phenomena that is observed with sigma with error of sigma. Mi here is defined as a linear relationship between weights and the the certain baseline value. Okay, so seeing that adding more and more samples, getting samples, we can see that those samples are generally really consistent. And when we plot a ribbon plot of the mean, so all these functions, we just compute the quantiles here, we can see that it's very well concentrated. When we add the prediction uncertainty, we can see that this prediction uncertainty is becoming is covering more and more of most of the samples available. So this gives our models a bit of credence. We can also see that our alpha and beta are rather concentrated here, so our very wide prior collapses to the very tight posterior here for alpha. Beta is also rather tightly constrained. And using this model, we can do multiple analysis. Except when we already created this functional relationship, we can, for example, see what is the mean height for the weight of 50 kilograms according to our model, and we can see that if for a person of weighing 50 kilos in this population, the mean height would be represented here, and we just do it by computing for each alpha and beta of our parameters. We use 50 minus the centering value, so we just start this, so we could cover it entirely in our interpretable range. We just use all of the values from alpha and beta, and for each of those we get the sample of the weight. So for each of those 4,000 samples of alpha and beta, which we use to compute for those histograms, we computed one estimate of the height. If you remember, or if you were taking attention, at start we just limited ourselves to the adult population. As you can see here, we just use adult population. So what if we cover entire population that is available, so also children? How well our model will work? We refit our model, and as you can see, there are changes. The relationship between weight becomes much more significant here than in case of alpha, and we can see that it does not capture the model at all. The relationship is significantly nonlinear. And so what? We cannot use linear models? Of course we can use linear models. We just need to add higher order predictors, so we can add functions of predictors. In our case, we can add additional value, or we can replace our linear relationship from weight into a polynomial one. In this case, a quadratic polynomial. So we have a quadratic relationship between mean and the weight. Again, we can use some prior predictive checks. We have our normal for our parameters. We are adding the normal. We are assigning again a normal prior, but and we assigned all values to do some computation. And from our priors, we can see that, well, it doesn't look that good, but we are not focusing on that now, because it's still most of the samples are still kind of in here, and the uncertainty for smaller weights representing standard deviations becomes even more, because somewhere here, if I'm not incorrect, we did some standardization here. Yes, we standardized the variables. I was covering too fast. Because we will be adding higher orders, we do not want the weight to be a bit get into large numbers, because squares of large numbers will become even larger. So we've moved to the to our model as a using the standard deviation. We are dividing our centered weight by standard deviation of the weight. In this case, gives us the values that are 97% will be between -1 and 1 for 97% will be between -2 and +2. So it will be smaller values. 67% give us -1 to +1. So in this case, the coefficients for square values will be in reasonable orders. As we can see, coefficients for beta is still, in this case, very wide, but because the variables are standardized, it doesn't make the model nonsense. When we move to a fitting, of course, we're just adding additional variables. A small change here, just changing the formula for the me by adding weight here and adding additional parameters, and that's it, and additional prior for beta 2. So technically doesn't change much, and we get a model that looks much better. So we can do complication of the model by adding higher order predictors here to get even better representation of our data. And we can do that even more. We can add, for example, additional predictors, let's say a third power to our standardized weight. So we can just add the first, second, and third power of standardized weight here, and we can construct something called the design matrix. Design matrix here is just we have a matrix which will multiply by the vector of parameters, which will have complementary sizes, and then our model moves to a traditional form of x beta plus alpha for each of the mu's. So mu are now represented by our in our model, and in this case it even becomes a bit simpler situation, because we can even assign for each of those variables a joint prior, which each variables in the vector of beta parameters will be assigned a similar normal prior. We are now just focusing on technicalities. We are not rethinking them too much. So, but as you can see, this change in adding predictors, it becomes even simpler. If we want to add multiple powers, we just increase the number of predictors, and we add we just add an additional columns to the design matrix. So from something from that, we get a model that is even better in kind of capturing this nonlinear movement. But again, we have an issue that does it model make sense? And here is an open area, for example, for using model comparison methods to see is adding additional predictors makes sense. Moreover, it add additional the added improvement corresponds to the additional uncertainty added by moving more parameters. So we are covering for potential overfit by introducing too many parameters. Moreover, the first model was at least interpretable. What is the interpretability of coefficients for square and third power of weights? Well, this is difficult. Here we have now generate some kind of assumption that there is a function that relates the weight to the height, but this relationship is really unknown, and we're just approximating it by a few polynomial terms, and actually we are not doing it in the most efficient way that we could. So that's the general idea of increasing the parameters. So let's move for a bit to the slides to generally cover a bit more. So in practice, using the design matrix is a typical idea how to generalize our model to make it more, let's say, understandable. Or not maybe understandable, but just easily implementable. So our vector of outcomes correspond to a normal distribution with a vector of means that is constructed by adding alpha to a design matrix multiplied by beta. And in this design matrix, we could have multiple parameters or functions, multiple predictors or functions of the predictors. They are often called, especially in machine learning, being called features of the data, because sometimes they can be just functions of measured time, let's say time series of data. When we, for example, want to create a model for predicting certain values, or for classification of not really values, but for example classification of faults by observing, let's say, waveforms of current from the electrical motor, then we can compute some features from this signal and use it in this design matrix to compute the relationship. But this, of course, doesn't end the ideas for the linear models, because we can have something called mixed effects models. And mixed effects models is, of course, one idea of complicating simple things, because beside predictors and intercepts, which actually can be even hidden in the design matrix, because if you add columns of ones to the design matrix, then the first coefficient of vector beta can just be your intercept. And this is very popular, for example, in scikit-learn. Scikit-learn does it exactly like that. They don't have a natural intercept in the model. But mixed effect models have a different idea. That besides our predictors, we can have also some random effects that are corresponding to certain other aspects of our measurements. So there are random effects beta that are influencing some of the observations. And Z matrix gives you which random effect influences our observation. And usually in a mixed effect models, we assume that beta has some kind of normal distribution, usually a multivariate normal distribution, so there will be some kind of covariance matrix. Of course, this can always be a diagonal matrix, and random effects can be individual with each other. It all depends on the problem. But this sounds a bit abstract. So move to something that may be also abstract, but less. Let's imagine a situation that we are measuring at different locations, which are neighboring each other in some kind of way, which can be represented as a graph. For example, these can be countries which have neighboring borders with each other. So we can assume that what's happening in 1 influences 2 and 3. We can assume in some kind of way. We can assume that what happens in 3 influences 1 and 2 because they are neighboring. But for example, 2 neighbors 4, 1 and 3, and so it influences all of them. 4 influences only 2 and 3, 2 and 5, and 5 influences only 4, because it doesn't neighbor any of the others. So, for example, if you want to do some kind of statistics corresponding to the, let's say, variability or virus transmissions between countries, we can assume that there are some kind of effects that increase the spread from one country to another, and there can be corresponding to multiple, like from physical borders or some kind of other connections. Representation using graphs is very useful in this way, or lattices or grids. So representing the relationships, and the popular option is the adjacency matrix of a graph, so which indicates which node of the graph is neighboring with which one. So for 1 we have ones, for the first one, first row we have 1 and 1. So in the second and third position, so it corresponds that this neighboring is 2. 2 is neighboring 1, 3, and 4. 3 is corresponding 1 and is neighboring 1 and 2. 4 is neighboring 2 and 5, and 5 is only neighboring 4. And we have, of course, the vector of random effects. What is important is a very simple, very small graph. In case of real graphs, for example, if you have multiple countries, or for example, voivodeships in Poland, or some kind of other municipalities, or you are modeling, let's say, in an electrical circuit, a spread of temperature. So you have these multiple connections that you have to model. So this matrix can be very large, and usually is very sparse. That is, from one corner we are not neighboring those here. All the neighboring effects go through the neighbors. So even if it influences from here, it has to go through entire path. So this matrix usually in bigger problems can be very sparse. And because of that, we can then construct our model, which will have typical linear path, and additionally, we have, for depending on which in which location the if measurement was taken, we take appropriate row of the matrix V and multiply it by vector of coefficient. E here is a standard unit vector that E1 is 1 on all zeros, E2 is 0, 1, all zeros, and so on. So we are just taking appropriate unit vectors in order to get appropriate row of V matrix. So the Z matrix becomes a large matrix with the appropriate rows of the V located one over another. And the again, if V is large and sparse, Z also will be large and sparse. But and usually we have much less locations than measurements, so this matrix will be large and will be a lot of zeros, and this perhaps will have to be modeled in what you are doing. So from Bayesian point of view, and moderates say this actually is not a big problem, what's happening here, because we can reformulate our problem into a simple linear model, because we can just take a matrix A, which corresponds to our design matrix X and our random effect matrix Z. We can create a new parameter vector that will compute our own original linear relationship parameters and random effects here, and we can then create our model here. The difference in mixed effects models comes from the fact that usually when we are not considering them in the typical Bayesian context, you had no priors for beta, you had no priors for sigma, and beta was the only thing with priors because of those random effects. When you have normal prior from beta, this actually becomes even simpler and can be realized with some linear algebra to simplify almost everything except non-normal priors. And such ideas are, for example, used in INLA numerical package that specializes in this kind of mixed effect models, which can cover a lot of stuff. And those mixed effects models can be generally treated as many vectors. But mixed effects models are very interesting. They are relatively simple for the small sizes. In large sizes, then you have to think about how to exploit the sparsity of Z, exploit potential sparsity of X. So how to create the model that will be numerically efficient, because if you are moving to one of the ideas that is being currently developed is to use the split the problem to a normal part, which can be realized mostly with linear algebra, and non-normal part, which requires Monte Carlo sampling. So you have Monte Carlo sampling on a small subset of parameters, and then you can cover from the rest using linear algebra, which is a big boon to the speed of computation. And generally that's how INLA works. INLA additionally approximates the non-normal paths with the Laplace approximation, but it's very efficient if the more normal the problem is. The more the priors are normal, the better results are being obtained. So generally this was to cover the linear models in the context of Bayesian analysis. Hopefully it wasn't too boring to you. There will be some more surprise streams in the future to cover for the missing lectures. I say it's a surprise from very simple reasons, because really I've decided that I'll do it as a live stream with all the problems with quality and stuff, but when I will do it, it will be there. If I just record it, then I will probably be tempted to, oh no, I have to edit this, and if I want to edit this, then the issue is that it will happen later, much later, to be presented here. So that's why if you are hopefully you will forgive me that you weren't notified earlier, but now the stream is available on my YouTube channel and you can watch it at your earliest convenience, and hopefully it will help your projects. I still have to cover a few stuff that I hopefully will. I have prepared the generalized linear models, which are waiting here, but I've especially took a bit more time, too much time with linear models. And I plan to do something on functional models, so splines, Gaussian processes, time series models, and I would love to do hierarchical modeling lecture. So possibly we'll be able to cover all of this before the end of semester, and I will be very happy to do it, but we'll see what happens. Thank you very much to all those listening. If you have any questions, getting for the time to answer, I'm just waiting a bit here, a minute, or maybe not a minute, like 30 seconds. If you have any questions, all those two people here, please do so. If you don't have any questions, then I wish you a very good afternoon. Sunday afternoon. Okay, I see no questions. Thank you very much, and goodbye.